Hello everybody, and welcome back to my SP2 channel. This video is all about ideal gas law. There's going to be an introduction. We're going to be looking at the ideal gas law equation. There's a little bit on the gas constant as well as the standard temperature and pressure, which is a very common conditions for our gas law calculations. I also have a little bit practice for you at the end. Okay, so if you remember in our previous lecture, we talked about a few of very common gas laws. One of them was the Boyle's law, and we mentioned that we have the pressure and the volume that are inversely proportional. We also mentioned about Charles' law, where we have volume and the temperature that are directly proportional. By Avogadro's law, we figured that out, that the volume and the number of moles of the gas are going to be always directly proportional as well, right? Now, I'm going to put all three of these kind of together. That is how we get the volume that is going to be proportional to the N, the number of moles of the gas. And then I have the temperature, right? These two are on the top, and then we have the pressure at the bottom. So this would be more like a proportionality relationship. If you want to turn this to an actual equation, we need to have a constant. So the constant that is connecting the volume to the rest of the stuff on the right side is going to be our gas constant, right? So this equation, the PV that goes to nRT, right? This is equation that what we call it as the master equation, right? Pretty much all the gas laws questions are somehow related to this very common, very important equation, okay? It's putting all of these gas laws kind of together. Okay, so I'm going to copy this on the next page, and we're going to be like talking more about, different units that we have for the R and a little bit more discussion on that. Okay, so follow me on the next page. Okay, so again, you have the PV on the left side that is equal to your nRT. So this is our master equation. And just a quick reminder, P here is our pressure, everybody, right? V is going to be our volume, as you know. N is going to be the number of moles of the gas that we have, right? We mentioned about the R, which is our gas constant, okay? And then we have the temperature that has to be always in Kelvin. For the rest of the variables, we have a few options. We have a little bit flexibility, right? And I'm going to talk about the units of R on the next page, okay? But I want to kind of emphasize, everybody listen up. The temperature units can never be anything other than Kelvin. There are many other options. We're not allowed to use them. For our gas law calculations, the T has to be always in K Kelvin, okay? So now let's talk about the R, right, which is our gas constant, and what are a few options for the units on the next page, okay? Okay, so as I mentioned, there are a bunch of different gas constant units, right? And here are the summary of them. So the first one is the 0.08206, and that is the one that we have the pressure in ATM and volume is in liter. The second one is 62.36. That's for the case that we have the pressure in torr or potentially in mmHg, right? And the volume is still in liter. Okay. The third one, this is actually the one that is pretty common, is the 8.314. And that's the one that we are typically working with, like the SI units. Okay. Then we have the 8.314, which is exactly the same. And that's the one that I have for the pressure of the Pascal and the volume of cubic meter. Okay. And then the last one is 1.987, where we have pretty much the energy units is in calorie, right? Now, don't worry about, memorizing this constant. Obviously, you do not need to do that. This would be given to you. But my recommendation is always double check and make sure that you're using the right one, right? The one that is properly matched with your units of other variables. Okay, excellent. Okay, now let's talk about the standard temperature and pressure known as STP. Okay, so this is a very common condition, very common for the gases and the gas laws calculations. And anytime that we say STP, we are referring to the very specific temperature and pressure. the temperature is going to be 0 degrees Celsius, which is almost 273 K, and your pressure is going to be always 1 atm or the 760 torr, which is almost 101 kilopascal. Okay, now I'm going to do a really cool practice. I'm going to assume that I have the SDP and I only have 1 mole of a gas. Okay, and now we'll try to figure out what is the volume of this gas. Okay, so because we are at the SDP, then we know exactly the temperature and the pressure. We try to solve it for the volume, so that is our unknown, and we only have 1 mole, so the N is going to be just 1. The R that we have to use here is going to be the 0.08206 because that is the one that is matching with the units of our variables. Okay, so do the plug and chug. Look at here. We are solving for the volume, so it has to be nRT divided by P pressure. Plug in all the values. Look at this volume. It's going to be 22.4 liter, and it doesn't matter what is the nature of that gas, right? It could be a hydrogen gas, it could be oxygen gas, whatever is the gas. As you can see, we don't have anything about the identity of the gas in our calculation. So that means as long as you are at the STP conditions, everybody listen up, as long as you're at the STP condition for all the gases, it doesn't matter what is the gas, if you have 1 mole of that gas, it is going to take up 22.4 liter. Okay, cool. Okay, so that brings us to our practice. You've got calcium carbonate, which is what we have in limestone, decomposes into calcium oxide and carbon dioxide. You've got a sample of that already decomposed. The carbon dioxide is collected in a 250 ml flask. The pressure of this gas is 131.72 kilopascal and the temperature is 31 degrees Celsius. The question is how many moles of carbon dioxide were generated. Okay, so I'm going to answer to this question using a few slides. Okay, so follow me on the next one. Okay, so step number 1 is writing the reaction, right? So calcium carbonate is producing calcium oxide and carbon dioxide. This reaction is already balanced, so you want to make sure that you're double checking you're balancing the reaction, and it is balanced, so we're good. Now, according to your stoichiometric coefficient, if you have 1 mole of calcium carbonate, that is going to be producing 1 mole of carbon dioxide. So we have 1-to-1 ratio here, okay? Now, I'm going to go ahead and gather all the information that are given by the question stem. And as you can see, you've got the pressure, right? You've got the volume here. You've got the temperature. Make sure that you convert that to your Kelvin, right? You also have this R, which is the one that is properly chosen based on the variables unit that we have, right? Okay, now, using the ideal gas equation, right, we are going to isolate that for the N. So it's going to be pressure volume divided by RT. So plug in the values. Now I'm going to put the numerator and denominator on the next slide, right? And I'm going to show you the actual values and how we do the division, okay? So take a look at the next page. Okay, so this is what I got from my numerator, right? So you grab your calculator and you do this. And then we have the same thing pretty much for the denominator. You multiply these two, and then you take this divided by that, right? And that is how we get the N, which is going to be our moles of CO2. Okay, I hope that makes sense. A very big thank you to all of you for watching this video. There are going to be a lot more coming up soon. Stay tuned for that. Take care of yourself and bye-bye for now.